In this video, we want to talk about an equivalent characterization of primitive cube roots of unity in finite fields. In other words, we want to show that if we find two elements in a field, in this case they are the elements 2 and 4, that are each other's square roots, as we have here, then these two elements are indeed primitive cube roots of unity, which we can quickly show here for this case. 2 to the third would be equal to 1, because we're doing this operation mod 7, right? So, and also 4 to the third would be equal to 1. So they are cube roots of unity. Now we need to show that they are primitive cube roots of unity. So strictly speaking, we'd have to show that 2 itself is not equal to 1, of course, and 2 squared is equal to 4, which is of course not equal to 1. The same thing we can show about 4. Quite obviously, 4 is not equal to 1, and 4 squared is also not equal to 1. But with that, we have now shown that 2 and 4 are primitive cube roots of unity. So let's write that out in a more general fashion so that we can prove it. So distinct elements, A and B, in some field F, are primitive cube roots of unity if and only if A equals B squared and B equals A squared. Before we prove this, let's talk shortly about this part, distinct elements. We shouldn't forget that, because if we have elements, for example, A being equal to 0 and B being equal to 0, then it is indeed the case that A equals B squared and B equals A squared, right? Everything is just 0. But these are not primitive cube roots of unity. The same could be true of the case A equals 1 and B equals 1. So in the one direction at least, we definitely need to remember that. In the other direction, as it turns out, we also need to know that. Because if we have A and B that are not distinct primitive cube roots of unity, we could have, for example, here, A is equal to 2 and B is equal to 2. So that would mean they are indeed primitive cube roots of unity both. But it is not the case that A equals B squared, right? That would mean 2 would be equal to 4, which is obviously not the case. So for both directions, we definitely need to remember that these are distinct elements. And with that, we can move on and actually prove this theorem. So let A and B be distinct primitive cube roots of unity in F. Now, since A is a primitive cube root of unity, we know that the set generated by A must include all the cube roots of unity. So it must be A and B and 1. So it includes only those 3 cube roots of unity. We also know about this set generated by A that it is indeed just A to the first power, A to the second power, A to the third power, and etc. And now what we want to know is which of these powers is the one creating B. So A to the first power is quite obviously the same as A. And A to the third power, since A is a cube root of unity, must be equal to 1. So A squared is the only one left over for B, right? Because if we were to continue this set here, it would start repeating, right? Since A cubed is equal to 1, then this would be, again, just equal to A. So, with that, we know that A squared is equal to B. And in the exact same way, we could show that B squared is indeed equal to A. So, we have already finished the first direction of the proof. If we find primitive cube roots of unity, then this will definitely hold that A is equal to B squared and B is equal to a squared. Now we want to show the other direction. So let a and b be distinct elements of f such that a squared equals b and b squared equals a. And I'm also going to write here that a is not equal to b, right, since they're distinct elements. And now we're going to use these three little nuggets of information to prove this direction of the theorem. So we'll start out by finding out something about a cubed and b cubed. So if a squared is equal to b, and I multiply both sides of this equation by a, I get a cubed being equal to ab, and in the same way, I multiply both sides of this equation by b, I get b cubed is equal to ab, which of course, taken together, means that a cubed is equal to b cubed, or for our purposes, a cubed minus b cubed is equal to 0. Now at this point, we are going to write one little chain of equations after another, all starting with 0, and we'll whittle away at this right here until we get down to a characterization of a in terms of b. So a is equal to a cubed minus b cubed, which we can factor is a minus b times a squared plus ab plus b squared. And now we need to ask ourselves if a minus b can be equal to 0, and we see our answer here. A minus b can never be equal to 0, since a and b are different, they are distinct. So that means this must be equal to 0, and we have another little equation here starting with 0. 0 is equal to a squared plus ab plus b squared. And now we look at this little nugget of information. We know that a squared is equal to b, so we can sub in here and say b plus ab plus b squared. We factor out the b and get 1 plus a plus b in parentheses. So now we need to ask ourselves, can b be equal to 0? Well, let's assume just for a moment that b is equal to 0. That would imply that b squared is equal to 0. And since we know that b squared is equal to a, that would mean a is equal to 0. So these two parts taken together would mean a is equal to b, which it's not. So we have a contradiction, and we see that indeed b is not equal to 0, which means this must be equal to 0. So we have another little equation here, and now we are at our goal. So 0 is equal to, I'll write that this way, a plus b plus 1. Equivalently, a is equal to negative b plus 1. And that is exactly what we wanted, a characterization of a in terms of b. So now we will show that a and b are cube roots of unity. Afterwards, we will then show that they are primitive cube roots of unity. So a cubed is equal to negative b plus 1 cubed, which multiplied out gives us negative b cubed minus 3b squared minus 3b minus 1. And now since we know that a cubed is equal to b cubed, we can sub in here, which gives us negative a cubed minus 3b squared minus 3b minus 1. Now I would have liked to write a 3 there. In fact, I'm going to do that, minus 3 and then plus 2, because I want to factor out these minus 3's. So now we put our a's on the same side of the equation. We get 2a cubed being equal to, Here I'll factor out the negative 3. Negative 3 times b squared plus b plus 1, and then of course plus our 2. And now we're at the point where we can recognize that b squared being equal to a will bring us the last step home towards our goal. So we can sub in here. We get 3 times a plus b plus 1 plus 2. That's a negative 3, isn't it? So where have we seen this before? A plus b plus 1. We saw that this was indeed equal to 0. So since this vanishes, we are left with 2, which means we can divide both sides of the equation by 2 and get a cubed being equal to 1. And since we know that a cubed is equal to b cubed, we also know that b cubed is equal to 1. So with that, we've shown that a and b are both cube roots of unity. Now, in order to show that they are not simply cube roots of unity without being primitive cube roots of unity, we need to show that a is not equal to 1, and theoretically speaking, we would need to show that a squared is not equal to 1. So if a, so that's what we want to show, right? So if a were equal to 1, that would mean, if we multiply both sides of those equations by a squared is equal to a. But we know that b is equal to a squared, so that means a is equal to b. But we know a is not equal to b, so we have a contradiction, and a must be equal to something other than 1. And a squared being equal to 1 would lead to a cubed being equal to a, and we know that a cubed, as we've just found out, is equal to 1. So that would mean, taking these two parts together, that a is equal to 1. But we've just seen that a is not equal to 1. So indeed, a is a primitive cube root of unity, and by the same token, we could show that in exactly the same way. b is also a primitive cube root of unity, and with that, we are finished with our proof. So, we've seen now that if we have distinct elements, a and b, if they are primitive cube roots of unity, then this condition must hold. A must be equal to b squared, and b must be equal to a squared. That's what we showed with the first half of the proof. And now we've just seen that if we do indeed find a and b with this condition, as long as they're distinct, then they must be primitive cube roots of unity. So now we should look at an example of each one of these cases. So let's look at the field f4, created with this irreducible polynomial. We see that x squared gives us x plus 1. And x plus 1 squared gives us x. So we have exactly that situation. So let's make sure that this is indeed the case, that x and x plus 1 are primitive cube roots of unity, which we can show very easily. X cubed is simply equal to x squared plus times x, and x squared, as we've just seen, is equal to x plus 1. We multiply that out and have x squared plus x. We divide through by our irreducible polynomial and determine quite quickly that indeed what's left over is a negative 1, but since this field has a characteristic of 2, that is, allows only coefficients of either 0 or 1, then negative 1 is the same as 1, and we've determined now that x is a cube root of unity, and while it is the case, let's say it this way, because we can easily show that x is not equal to 1, right? These are not equal. And x squared, which is x plus 1, is also not equal to 1. Then we know that x is a primitive cube root of unity, and we could show in the exact same way that x plus 1 is indeed a primitive cube root of unity. So we've looked at this direction here. We started here, and we showed that this is the case. So now we'll take a look a little bit at our proof here, and we'll call to mind everything that we used in order to prove this, and we might realize that nowhere did we ever use the assumption that we are dealing with a finite field. So this must be also true of infinite fields. For example, the complex numbers. So we see here the unit circle and the 3 cube roots of unity indicated, forming an equilateral triangle. And I've labeled the one primitive cube root of unity A and the other one B. And so what we now want to know is whether a squared is indeed, I'll write it 2 for squared, b, and whether b squared is indeed a. So a is not equal to b. So right, we need to know that. Right, we have a plus here and a minus here. These are not the same. They are distinct. Now if we write out a squared, multiply that out, simplify, indeed we get b. And if we do the same thing with b squared, we write it out, we multiply it out, and we simplify, indeed we get a. So we've now seen an example of this direction of the theorem, that if we have primitive cube roots of unity, then a must be equal to b squared and b must be equal to a squared as long as the elements indeed are distinct. So we could also ask the question now, well, what about other fields? What about other infinite fields? What about the real numbers, for example? Does our theorem tell us anything about the real numbers? Well, on the one hand, we could say, well, it doesn't really apply to the real numbers because a cubed being equal to 1 directly implies that a is equal to 1. In other words, there are no primitive cube roots of unity in the real numbers. But that in itself does tell us something, doesn't it? Because of the if and only if nature of this theorem, we know that if there are no primitive cube roots of unity in R, then there must also be no elements a and b such that a is equal to b squared and b is equal to a squared. So that's maybe something interesting to know. And our theorem told us that, although at first sight you might think it tells us nothing about R. But indeed it does. So that was the equivalent characterization of primitive cube roots of unity in all fields.